Hello?
Yeah, hi Emily.
Hello.
How are you tonight?
Good, how are you?
Good. So are we doing ACT or are we doing more algebra?
We're going to be doing more algebra today, but my mom's scheduling more sections so we can work on the ACT because I'm doing the ACT in October.
Okay, sounds good. What do you got in the way of algebra tonight?
Alright, so the algebra, linear programming.
Okay.
And the first question is, the area of a parking lot is 600 square meters. A car requires 6 square meters. A bus requires 30 square meters. The attendant can handle only 60 vehicles. If a car is charged $2.50 and a bus $7.50, how many of each should be accepted to maximize income?
All right. Well, let's talk about the objective function, which is the function that is income, since that's what we're trying to maximize.
Oh, and then they gave me a graph at the bottom.
Okay. Well, first of all, let's define what our income is going to be.
$7.50 for buses and $2.50 for cars.
Okay, so cars times 250 plus buses times 750. So that's our income that we're trying to maximize. And we also know that the total square footage of the parking lot is 600. So we can say cars times 6 plus buses times 30 has to be less than or equal to 600 square feet. We also know that cars and buses have to be less than or equal to 60. Okay, so these three equations or inequalities are what we have to start with. You with me?
Yep.
Okay. Well, the way you do linear programming is you graph basically both your inequalities and you examine the vertexes of your graph to determine which one produces the highest income.
Okay.
So let's graph the easiest thing we can graph. C plus B has to be less than or equal to 60. So let's see. If I put C there and B there, then if C is 0, B is 60, I could have 60 buses. But if B is 0, I'm going to have 60 cars. So that line represents that inequality.
Yay.
Now, the second inequality is that each car takes 6 square feet, each bus takes 30 square feet. I only have 600 square feet. So let's graph this. 6 times C plus 30 times B is less than 600. Well, that graphs as, let's see, when B is 0, I could put 100 cars. Go down a little bit here. Let me redraw this thing. So one inequality is this. I have to be on the left side of that inequality. And the other inequality is, let's see, when B is 0, C is 100. When C is 0, B is 20. So I got that point there, and I got that point there.
Can we do that again?
Yeah. This inequality is 6C plus 30B is less than or equal to 600. This constraint is C plus B has to be less than or equal to 60.
Okay.
Okay.
And then we can divide
the fact that I have to be less than means that if I had to shade one side of that one, it would be that side. If I had to shade one side of that one, it would be that side.
So it'd be in the middle part, which is those 4 lines.
Yeah.
But don't we have to graph the other one?
Oops. Hold on a second.
All right. I'm writing stuff down.
The income function is what's going to tell us, in other words, what we have to do is to look at this picture. Is this the graph that they gave you?
Yeah, they gave me a graph, but it only had the top right-hand corner of the graph, the positives. And they didn't give me any of the points or anything that was on the graph. It was just a graph that goes 20, 40, 60, 80, 100, 120.
Okay. With linear programming, what you do is you find the common area and you check the vertexes. In other words, I want to check that point, I want to check this point, and I want to check this point. And it's been a while since I've done these. Bear with me for a second here. I got to remember exactly how you want to do these. But
Absolutely.
what we now want to do is figure out which of those vertexes produces the highest income. Well, the income function is 250C plus 750B and that maximum is going to come at one of these vertexes. Well, let's examine that vertex. We can have 100 cars and no buses. So the income of the first vertex, which would be 100, 0 buses, 100 cars, would be $2,500, correct?
How do you know?
No, 250. Well, because we get 250 for each car, and we get 0 for the buses, because we're going to have all cars. In other words, if I examine this vertex right there, that is the car axis, this is the bus. And they may have drawn it opposite on your diagram. I could have put cars on the horizontal and buses on the vertical. It wouldn't have mattered. But basically what I'm interested in examining is this point, and this point. The maximum income is going to be earned at one of those points.
Got it.
Okay. Well, let's examine this point. What would be the income if I have 60 buses and 0 cars? Well, what's 6 times 7.5? 450? So that would clearly be more income than 100 cars, right?
Yes.
Where did I get 100 from? You couldn't have 100 cars. You can only have 60 cars.
All right, I'm started right now graphing the second equation. Do we have to graph the third equation?
No, we don't. The only ones you have to graph are the constraints. And we only have 2 constraints. The constraints being the amount of square footage in the parking lot and the total number of vehicles that we can get into the parking lot. And they've told us that you can only get 60. So I did this first one wrong. That would be 0 and 60. And this would be 60 and 0. In other words, this is buses, this is cars. So if I had 60 cars, my income is going to be $150. If I had 60 buses, my income is going to be $450 because I get 3 times per bus. Problem is that can I put 60 buses in there? No. In other words, this constraint right here tells me that the most buses I could put in there is 20 if I had no cars at all. And that is this point. Hold on a moment. That's this point right there. I could put 20 buses in there and no cars. So what would that give me in the way of income? If I make this figure 20, in other words, that's one of the vertexes, well, that's the same amount, 150. So if I had 60 cars and no buses, I would have $150. If I had no cars and 20 buses, I would have $150. Now, those 2 points are right there. That's the 60 cars and no buses. Excuse me. And this is all cars, no buses, this is all buses, no cars.
So they equal the same thing. So you could have
We
all
do.
buses or all cars, and
Right.
you'd get
There's
100.
one other point we have to examine, and that's that point right there, which is where those two lines meet. Where do they cross? It's when C plus B is equal to 6C plus 30B. Hold on. Let me think for a second here. What is this point right there? That is, let's see, if I had C plus B equals 60 and 6C plus 30B equals 600, and I solve that by elimination to find out what that C and B point is, then I'm going to multiply the top equation by -3. Hold it, this is 30. Let's multiply the top equation by -6. Let's multiply, or we don't need to do anything to the bottom equation. Now I can add those two together, and I get 24B equals 240, so B equals 10. And if B equals 10, then C equals 50, because B plus C equals 60. Now at that point, we need to plug into the objective function to see what that produces. In other words, I want to know what my income would be if I had 10 buses and 50 cars. Well,
And we put that in by
we go back to the objective function, this function right here. And if I had 10 buses, that'd be $75 in buses. If I had 50 cars, that would be $125 in cars. That's $200. That's the answer.
Awesome.
In other words, that point right there produces $200 in income. This point here produces $150 in income. Or actually, it's this point, 60 cars and no buses. Yeah, the final picture that you're going to have here is going to look something like this. And that is 60 cars. That is 20 buses. And this point right there is 10 buses, 50 cars.
Yes, that's what I have. That's good.
And those are the three vertexes that we need to examine. In other words, when you're doing linear programming, your maximum always comes from one of the vertexes. So I don't need to examine this point there because I can't have 100 cars. I don't need to examine this point here because I can't have 60 buses. The constraints that they gave me limit me to this picture over here. And I merely need to plug in each of these points into my objective function, which is my revenue, to determine which one is the max. And usually they also say plug that one in, but that point is 0 buses and 0 cars, and that produces 0 income. So I don't need to check it. That's going to be a minimum. But if I'm looking for my minimums and my maximums, they're all going to appear at one of these vertexes. Okay?
Okay.
Hope that answers the question.
That did answer the question. It plugs in all the parts.
Linear programming is interesting. It's the toughest part of Algebra 2. Without doubt.
Really good to hear.
And yet they give it to you in the second week of Algebra 2.
Yeah, everyone's super confused. We had homework on it last night, and it was since last night was Sunday night, and everyone got to school and he's like, all right, raise your hand if you did the homework. Yeah. And everyone's like, well, I attempted to, but it was just no one got it.
It's tough. It's really tough. I'm always a little disappointed that they start out Algebra 2 with linear programming. They should put it at the end of Algebra 2.
I agree.
After you've done everything else that's a little easier, then you can get the linear programming. But it's difficult. The concept of linear programming is to figure out what your objective function is, and it's usually the function that you're trying to maximize or minimize. Some linear programming problems might be minimizing, okay? But if you're maximizing, then define your objective function, which is your income in this case, and define your constraints, which are the square footage and the number of vehicles. Graph them all on a chart, and then find your vertexes. Now, our original chart went way up like that, and way over here like that. But if we want the feasible possibilities, like I said, you cannot have 60 buses because that violates the square footage constraint. And you can't have 100 cars because that violates the total number of vehicles constraint. So basically, here, let me explain this a little bit better. We had two functions. One went like that. The other went like this. And it's this area here that is the feasible realm of possibilities. This area up here violates one of the constraints. So does this area over here. So those aren't possible. The only possible answers for vertexes are that one, and that one. And those are the only 3 points you need to plug into your objective function.
Awesome. Now I know. Do you think we can go over one more?
Sure, we can try.
All right.
Go ahead.
A store plans to sell expensive trees at Christmas. The supplier charges $80 for each real tree and $160 for each artificial tree. The store can buy between 20 and 90 real trees, inclusive, and up to 100 artificial trees. The supplier can buy between 40 and 120 trees total, but requires that the number of artificial trees ordered be more or equal to 2/3 the number of real trees.
I don't know if we can do this problem in 4 minutes, but I can give it a shot to at least set it up. Let's see. Let me make sure I got my constraints possible. The real tree's cost is $80.
Yes.
The artificial tree's cost is $160.
Yes.
You can have between 20 and 90 real trees, and you can have up to 100 artificial trees.
Yes.
What's the other constraint?
The supplier can supply between 40 and 120 trees total.
So real trees plus artificial trees have to be greater than 40 and less than 120. Do I have that right?
Yep.
And real trees have to be greater than 20 and less than 90.
The store is short of cash this year. Oh no. But requires that the number of artificial trees ordered must be more than or equal to 2/3 the number of real trees.
So it has to be greater than that. So there's one constraint, two constraints, three constraints, four constraints. What is the goal?
The store is short of cash this year and wants to invest in the minimum feasible amount in trees. How many of each kind should the store buy? So how many of each kind of trees should we buy?
To minimize the cost.
Minimize the cost.
And this is not a maximizing profit. This is a minimizing cost. Well, again, we are going to graph these. The objective function looks to be 80 times RT plus 160 times AT. That's my cost, right?
Yep.
So that's the objective function. Now, let's see if we can graph each of these other things. I'm going to try to do it. Let's see. If I make artificial trees that axis and real trees that axis, artificial trees, or if I plot the slope, let's change my axis. Let's make this AT and that RT here. In other words, Y is AT, X is RT. So Y equals 2/3 X. That would be a slope like that. So that's number one. AT has to be greater than RT, which means we're in this area here. With me?
Yep, so far.
Okay. Number two, RT has to be between 20 and 90. So RT has to be somewhere in there. Number three, AT has to be less than 100. So AT has to be less than that line. And finally, RT plus AT has to be greater than 40, less than 120. Well, that's the same as saying X plus Y has to be, so if I said X plus Y has to be greater than 40 and less than 120. So Y has to be greater than 40 minus X.
How do we make these equations?
What's that?
How do we make these equations? So the next equation is y is greater than 40 minus x.
Yeah, in other words, in my drawing here, RT is the x-axis, AT is the y-axis. So if I want to graph that, I actually have two equations. I have y is greater than 40 minus x, which is that line, and it's above that line. And I also have y is less than 120 minus x, which is that line. Y is less than 120 minus x. So it would be in this area here. And when we're all done, we're going to have an area that defines our possibilities. And we want to check the vertexes of each of whatever that area is. Now, this is so complicated that I'm not sure I can draw the figure accurately enough in the space that I have here. You understand how I graphed that?
Yes, but I think I did it wrong. How did 40 go to 40? Wait,
Well,
what is
AT is y, so y is greater than 2/3 x. If you graph that line, y is greater than 2/3 x, it's this line right there. Y is greater than 2/3 x.
I got that line.
Everything above that line. Okay, so that's the inequality number one.
So is this going to have 5 points?
Perhaps. I don't know. It's hard for me to see it at this point. First of all of the points of our final shape have to be above this first line here. It'd be nice if I had multiple colors. Let me kind of try to do this again here. So this is the area from the first equation. That's artificial trees have to be greater than 2/3 of real trees. In other words, you can't have 50 and 50. You with me?
I think I just got it.
Okay. If we go down, equation or inequality number 3 is artificial trees have to be less than 100. Well, here's the 100 line, and it has to be less, so it's in this area. Okay. The second one says real trees have to be between 20 and 90, so that would be that area. Going all the way up. I'm trying to use different things here so we can figure out. In other words, when we're done, there's going to be a portion of this graph that satisfies all 4 of these inequalities. And the final inequality is this x plus y has to be greater than 40 and less than 120. Well, that's the tough one. That means y has to be greater than 40 minus x, which is a slope of -1, has to be greater than And also y has to be less than 120 minus x. Well, y has to be less than 120 minus x. So that's that area. So assuming I had 5 different colors, instead of vertical lines, horizontal lines, slanted lines, you know what I'm saying?
Yeah.
Okay. If I had 5 different colors, then I would find the shape that all 5 colors were in. I can't really tell, but let's pretend. In other words, I don't have really the time to do it all, but let's pretend that's our final color. In other words, this area inside this triangle satisfies all 3 conditions. AT is greater than 2/3 RT. RT is between 20 and 90. AT is less than 100. And RT plus AT is greater than 40 and less than 120. So that shape right there. You see what I'm pointing at?
Yes.
Okay, we need to go to each of these vertexes and figure out what the cost is based on our objective function, this cost right here. So I need to find this point, plug it into the cost function. I need to find this point, plug it into the cost function, and I need to find that point and plug it into the cost function. Whichever one produces the smallest cost, that's your answer.
Wow. All right.
This is this is really a tough one here.
Yeah, I don't know. And it went from substitution to this, and wow.
I've seen a lot of linear programming problems, and this is the toughest one I've seen. Mainly because there's 4 different inequalities that have to be graphed. And one of them is this one here, which is particularly tough to graph. But once you graph them all, I mean, you're familiar with if I have an inequality and that's one, and this is another, and I have to be left of this one, and I have to be below this one, then the area that I'm concerned with is the area that's covered by both.
Yes.
Well, that's what you're going to do with every linear programming problem. You're going to graph each inequality, shading the appropriate side, and then you're going to find the shape that all your shading is in. In other words, this trapezoid that I just drew here, it's not even a trapezoid, this quadrilateral, is what you would get with just 2 inequalities. And then if I had an objective function, I would find out what that point was, what this point was, what this point was. Plug them all in, whatever gives me the maximum is my answer. Or in this case, since the objective function is to minimize your total purchases, then I would examine the vertex of my shape, and whichever gave me the lowest number would be my answer. Always remember the objective function is going to be whatever function is to be either minimized or maximized. In this case, we're minimizing it, but it's still, the cost is $80 per real tree and $160 per artificial tree. So you might say, well, why not get none of both? That's a cost of 0. Well, we can't do that because, for one thing, we have to have between 20 and 90 real trees. We have to have less than 100 artificial trees, and the sum of both have to be between 40 and 120. So all of these constraints define this final shape. And then, of course, determining what these vertexes are is also hard. In other words, what is this point? How many real trees and how many artificial trees is that point? Well, you have to solve some of these to figure out what your vertexes are. Just like in the first problem we did tonight, we had to equate the two constraints to figure out where that middle vertex was. If we go back, in other words, figuring out this spot right here, the only way we could do it would be to set this constraint equal or solve these two inequalities to figure out what that intersection point is. And I do that by turning them into equations and solving a system of equations. Okay? Realize we went beyond 30 minutes here. But that's okay with me. Unfortunately, I do have another session coming up, so I am going to have to go here. But
all right, well, thank you very much.
Yeah, I hope I've helped.
You have. And then the first one that we did, I wrote down very clear instructions about what you're supposed to be doing, so I can do the rest.
Okay, cool. And like I said, you really just have to measure all vertexes. Even the first one, we should have figured out the cost there, the cost there, the cost there, and the fourth vertex is 0, 0. It's just usually when you're maximizing, that's never going to be your maximum. But when you're minimizing, you want to do all vertexes. Now, I assumed that what we had here was a triangle. It may not be a triangle. This final shape that we end up with here may be a quadrilateral. And if it's a quadrilateral, then you have to figure out all four vertexes of that quadrilateral and test each one to see which one gives you a minimum cost. All right, Emily, I will let you go, and I will talk to you the next time.
All right, talk to you next time. I'm scheduling more stuff soon.
Okay, bye-bye.
Bye-bye.